So it's a pleasure to introduce my guest this evening to talk about the history of planet Earth, which is a fascinating topic, and to do it in a whistle-stop 45 minutes over 4.5 billion years of history is pretty amazing. So yeah, hold on to your seats for this. Paul Gannon is a science and technology writer, and he's an award-winning author of a code-breaking book from the First World War. So he's got specialism in code-breaking and writing, but he's also a science communicator, and he's written the fascinating series called Rock Trails, which is geological history aimed at the kind of mountain leader or the hill walker, really. So very accessible, very good communicator of geology. And it's a pleasure. Well, he and I have also co-authored a book on the outlook in the geology and the ecology. So yeah, we've worked quite closely over a number of years. So it's a pleasure to introduce Paul to talk tonight. If you have any, I'll be in the background. So if there's any issues, just put them in the chat function. The talk will go on 45 minutes, about 50 minutes. So there will be some time for questions and answers at the end of the talk. So put them in the chat and I'll field those to Paul. But for now, enjoy, and I'll hand over to Paul.
I need the green. Okay, I've got it. Okay. I hope everybody can hear me, and I hope that you can see on your screen the introduction with two pictures of the Earth. One that I took 4.5 billion years ago, and the other which I took 45 minutes ago. So welcome this evening, a nice evening to talk about this story. It's a bit of an experiment, really, different from the other webinars I've done, which have concentrated much on the geology of the last few 100 million years. But today we're going to try and look at a massive amount of time in 45 minutes. Oh dear. Okay, that's got it. Okay. Just to start off, I will point out that I've got on each slide, I've got a number, which is the number of the slide, which is purely for my information, really, to try and keep in touch with my notes and which I'm supposed to be talking about. But I've also put the age of the Earth on the top left-hand corner and how many years ago it was in billions or millions on the top right-hand corner. So you just keep up with the how long ago these things were happening that I was talking about. So to start on the subject proper, I'm going to say that the story of the Earth has always been one of constant change. So our 45-minute story will really concentrate on change. No, I've got it. I'm getting that noise again. Okay, I found out a way of doing it. As has been said, planet Earth is a restless, evolving planet. And as we shall see, for much of its time since the Earth was formed 4.5 billion years ago, its story has been intertwined with the story of life. The rock record reveals how the natural world, both living and non-living, has transformed itself again and again. And one thing I want to point out is that the Earth is the only known planet with oceans of water and an atmosphere rich in oxygen. In this sense, it is unique. This unique planet formed about 4.5 billion years ago, taking about 1 million years for planetesimals and other material to coalesce under the pull of gravity. But in those early days, the Earth was accompanied by a companion planet, or a moon, which was about 30% of the size of the Earth. This collided with Earth early in its history. Precisely when is not certain. This massive collision knocked the Earth with such force that it knocked its axis to a tilt of about 28 degrees, and the Earth absorbed a substantial chunk of the moon. The post-collision moon, therefore, was much smaller, was volcanic and closer to the Earth than it is today. Also, the Earth had a 5-hour day as it rapidly revolved. So this combination produced monster tides of molten magma sloshing around the Earth's surface on this rapidly revolving planet, adding more heat and keeping the surf molten. So for the first few million years, the Earth was, it is reckoned, a red-hot sphere torn apart by towering volcanoes with magma eruptions. And over time, it slowly cooled and changed into hardened black rock with sulfurous volcanic eruptions, rivers of red lava, and with the young planet being bombarded by asteroids and comets. Well, it has to be said that in fact there is little absolutely positive real evidence for the first 500 million years of the Earth. The next development, the next change, was these volcanic eruptions continued emitting CO2 and other gases such as steam, H2O, nitrogen and sulfurous compounds, creating a greenhouse atmosphere. And as the Earth slowly cooled over a few million years, the H2O changed from steam to surface water, forming the first oceans. And the surface crust developed, cooling to form a rock known as basalt. Basalt is still today the single most common rock type on the surface of the Earth because it exists under all the oceans. The crust that developed was probably about 75 kilometers deep, and its base would melt to form molten magma, which being less dense than the solid basalt, would then rise toward the surface, feeding countless volcanoes. Just to point out that the atmosphere represents just 1 part per million of the Earth's bulk. And it's been said that the Earth was not a pleasant place. It's been described as likely to have been a global tempest of dark clouds, howling winds, shattering lightning strikes, and unceasing torrential rains. So a bit like Wales in the last few weeks, actually. A couple of figures: the Earth's surface water, the oceans, account for just 0.02% of the Earth's total mass. And it's calculated that the upper mantle within the Earth, just the upper half of the mantle, contains perhaps as much as 16 times as much water as the oceans. And the Earth's core, made of iron, contains probably about as much as 80 times as much water as the oceans. But with time moving on, the atmosphere developed and the Earth's surface had cooled, was wet from the oceans, a brilliant blue water world with 1.5 kilometer deep oceans and white wisps of clouds, but with no continents, unlike this picture, which obviously is a modern one, which I've borrowed. However, on the surface, a new development started to occur as molten basalt formed at the base of the crust rose up and cooled on the surface to form granite islands, the very first tiny proto-continents with their volcanoes. This is a picture of modern granite, and the key here is the partial cooling of the magma. Different minerals within the magma solidify as it cools at different temperatures. So some will start to solidify earlier than others. And granite, the minerals that make up granite, are amongst the first to start to solidify. Granite is rich in silicon dioxide, which is a strong, resistant rock, unlike basalt, which is much more easily eroded by chemical and weather and physical weathering. As well as the silicon dioxide, granite contains 2 types of feldspar and a lot of iron-bearing minerals such as pyroxene or mica. As the magma cooled, these were among the first mineral components to cool, thus forming the granite islands with volcanoes. And as I said, these were said to be the first smatterings of the continents. The next major development to occur was that of the role of plate tectonics in the Earth's history. And we'll look at a little bit of detail of plate tectonics. And what we have is, in the mantle, the orange part, we can see these enormous great convection currents which bring heat up from the core, a hot, very hot core, towards the surface where it cools and erupts due to reduced pressure at ridge lines in the middle of the oceans. And then, as you can see from the arrows, the Earth's, the crust moves outwards until it collides with another lump of crust or parts of continents, and subducts underneath the Earth's, underneath the other plate. So we have here how and where the continents are made. In our subduction zone, we have collision with the granite islands. We also have volcanoes being created beneath the subducting oceanic plate, and also scraping off of rocks at the trench area of the subduction zone. So combined, these three elements contribute to the building of the continents. Slowly, the continents get bigger and bigger. So they can be anything up to 3 billion years old. The other thing to notice, however, is that our oceanic plate, because it subducts, it never gets more than about 200 million years old before it is recycled back into the mantle. So we've got a whole series of processes occurring which are slowly building up the size of the continents. And this started fairly early in the Earth's history, about 500 million years it started happening. Then along with plate tectonics, there was another critical development, which was the arrival of, or the development of, life on the planet. Now, there is no full agreement between geologists about when life began. There's hotly disputed timings for it, but at some point quite early in the history of the planet, simple or primitive forms of life developed, initially deriving energy taken from the rocks themselves. And just as there is no complete agreement on when life began, so there is no precise definition of what life is. But this NASA definition of a self-sustaining chemical system capable of undergoing Darwinian evolution is a working definition, although it might be so loose as to be rather meaningless. That will be argued by some people. Now, I'm leaving my comfort zone. I'm much more comfortable with the rocks than I am with life. So I hope I don't get too much of this mistaken and point out any errors in the question time. Now, as I say, there are various theories on the origins of life. A common feature of them is the involvement of carbon atoms, which possess an unmatched ability to bond to a variety of other atoms. All of the Earth's great transformative powers, however, it is believed, water, heat, lightning, and the chemical energy of rocks were brought to bear in life's genesis, and maybe it had multiple sources of genesis as well, not rather than a single one. So some of the simplest life from the beginning was what we might call slime, cyanobacteria, algae. These algae have survived because colonies of algae will put out basically a hard surface, a mat of carbonate material in which they live. And then when they die, the hard carbonate material is preserved. This example is much later than we've been talking about. This example is about 300 million years old, from the Carboniferous period in the Carboniferous limestone. And another survivor today of some early developments was the stromatolites. And they are important because they're an example of another major development in life, namely photosynthesis, so that the plants take in the energy of the sun, and in chemical processes, they emit oxygen. So we start to see an oxidation of the atmosphere. However, that oxygen is absorbed initially for a few 100 million years by iron in the rocks. And we get what's known as the banded iron formation, which is quite a common feature. These are very old rocks. And the theory here is the photosynthetic bacteria produced, perhaps for the first time in the young Earth's ocean, this free oxygen which oxidized and dissolved the iron that existed abundantly at the time. The oxygen combined with the dissolved iron in this Earth's oceans to form insoluble iron oxides, which precipitated out, forming a thin layer on the ocean floor. Now, the formation of the abundant banded iron formations only stopped once the majority of the iron from the oceans were used up, which resulted in the buildup of oxygen in the atmosphere, finally, as also suggested by the first appearance of common continental red beds of the post-BIF Earth, the post-British banded iron formation Earth. So the stripes we see represent alternating layers of silica-rich chert and iron-rich minerals like hematite and magnetite. This mixing triggered the oscillating production of iron and silica-rich minerals, which were deposited in layers on the sea floor. Then banded iron formation lasted for about 600 million years. So the result of the banded iron formation is that the level of the oxygen in the atmosphere didn't increase until all the iron beds had been oxygenated. We then move into a new part of the life of the Earth, which is sometimes called the boring billion, because its change occurs, but it's a rather less active amount of change than we've been looking at so far, a time of relative biological and geological stasis, but combined as well, mind you, with the slow expansion of the role of continental rocks. And then with the production of the red planet with enormous deserts. We then had another important development occurring during the boring billion, so-called, although not all geologists subscribe to such a tabloid headline for the subject. But the important development was the development of the first supercontinents, where all the continents joined together, brought together, formed a supercontinent for a few 100 million years, then broke up, and the fragments of continent moved around the Earth's surface, then combined again to form another supercontinent a few 100 million years later. And when they combine together, they collide into one another, form mountain ranges, and form a pseudo where they're joined until they begin to pull apart again. So one of the major, the first supercontinent was Columbia, as it was called, 1.9 billion years ago. A hot, dry interior, no vegetation, lots of red deserts. And that stayed as one large continent for about 300 million years towards the beginning of the boring billion, before beginning to break up. About 1.2 billion years ago, Rodinia, the second of the supercontinents, forms during the boring billion. Rodinia being the Russian word for Earth. We then get on to another. We start to move out of the boring billion, and we move into the period known as the snowball Earth, although again, these are often very challenged descriptions. Some call it the slush ball Earth. And the first feature that we saw in the snowball Earth was the breakup of Rodinia, which produced more coast, which meant more algae, more burial of carbon dioxide, and a reduction in the greenhouse effect. So leading to cooling, the decaying biomass consumes oxygen, but the biomass instead becomes locked into the carbonate rocks, creating the hothouse cycle. With continental breakup and reassembly, radical climate swings occur on an epic shift in the ocean and atmospheric chemistry with the rise of plant and animal life. So we've got our snowball Earth, sort of snowball hot ice cycle, where conditions encourage the growth of ice to cover nearly all of the Earth's surface, locks the Earth virtually into a covering of ice which reflects the sunlight, which intensifies the cooling. And there was a possibility that the Earth could have become a constantly snow, ice encrusted planet. However, plate tectonics came to the rescue, so to speak, because volcanoes continued to erupt as plate tectonics wasn't affected by the snowball conditions, and it emitted CO2, which led to atmospheric warming and the melting of ice. So we had snowball conditions between 750 and 720 million years ago. We're at 650 million years ago, and the last time at 580 million years ago. And at that point, we start to enter what is known now as the Ediacaran, if I've got the pronunciation correct, period, which ran from about 635 to 550 million years ago. And we're getting close to geologically recent times. And during this period, we start to see levels of oxygen in the atmosphere begin to approach modern levels. And we also see the formation of complex life with lots of soft-bodied animals in the Ediacaran fauna, which has become quite famous, although most of it died out. So we're beginning to look like a familiar Earth now, the blue, green, white Earth with the continents. So from around 650 million years ago, the Earth's continental surface begins to become green. And we see what's often called the explosion of life and the variety of life forms of animals and plant formations. And we also see the formation of a supercontinent, Pangaea. And in the formation of that supercontinent, Pangaea, we have a collision of various continental lumps, continental fragments, and they produce the mountain building phase known as the Calanides, which is the one which we're most familiar with because it includes our Welsh, Lakeland, Scottish, and many of the Irish mountains. So we're beginning to get towards areas where we're familiar with. Then after a few million years, we get the breakup of Pangaea, collisions break up, and we see collisions between the broken off parts. So Europe is collided into by Africa or an arm of Africa to form the Alps. India collides into Asia to form the Himalayas. And we also see mini ice ages, nothing like the snowball life events. They're familiar mini ice ages, and we're meant to be in a warm period between two ice ages. We also have quite rapidly now, when things are beginning to happen quite fast, we've got plants on land, first as rootless, ground-hugging, green descendants of green algae, and which survive only in low, wet places. But from about 430 million years ago, the development of species similar to modern mosses and simple vascular plants, the oldest known plant fossils indeed, from this time. And then, as I say, things begin to start happening quite fast. By 400 million years ago, we get vascular plants, spindly, leafless miniature shrubs with greenish sun-seeking photosynthetic stems and leafless branches a few centimeters tall. And also some odd ones, the prototaxites, which are 3 to 4 meters high, tree-like plants, but actually a giant fungus. And also a few small land animals, insects and spider-like animals. And from about 360 million years ago, with the continents beginning to turn green, with tree-like ferns, though as yet no vertebrates on land. We also get the first land-legged animals from about 340 million years ago, and the first true amphibians in swampy land and dense green forests in the Carboniferous period, with lots of decaying plants captured in coal, so not breaking down, not releasing the carbon that they contain, so the oxygen level in the atmosphere rises to a higher level than it is today, of 30%. Today is around about 20%, just over 20%. And so we begin in this Carboniferous period to get the first true trees, fern-like trees, about 40 meters tall in this example, the Lycosipid or Lycopicid. Not sure of the pronunciation again. And this is, as I say, in the Carboniferous period when we had the first forests and swamps, and where vast amounts of coal were collected from the decaying plants captured in the water on below the vegetation. And as I say, the oxygen atmosphere rises to about 35%. And we begin to get quite common in the Carboniferous period in places like South Wales, the Pennines and so on. We begin to find lots of plant fossils, and these you can find still today scattered on the top of the soil. So we've got lots of decaying plants being captured in the coal and the oxygen level rising to almost 30%. And one consequence of that was development of giant insects, dragonflies with 75-centimeter wingspans, and creepy crawlies, to use the scientific term, about 70 centimeters long. Once again, not a nice environment for human beings to have lived in. Fortunately, we hadn't developed at that time. However, then around about 251 million years ago, there occurred the Great Extinction event. About 70% of land species and 96% of marine species disappeared. And there's no agreement on the cause of this Great Extinction event, but it was probably not a single factor that caused it. Oxygen dropped to about 20% of the atmosphere. There was atmospheric cooling, large-scale volcanism, million-plus cubic meters of basalt erupted in Siberia, and these eruptions led to the sun being blocked, not getting through to the Earth. So the conditions of life were fundamentally altered, and it led to this Great Extinction event. However, it led to new flora and fauna being evolved to fill the vacant niches. And around 230 million years ago, dinosaurs started to appear, as do ammonites, flowering plants, and small mammals. About 65 million years ago, a 10-kilometer wide asteroid strikes the Earth, causing a mega tsunami, massive fires, the Deca Trap eruptions, again vast amounts of basalt are erupted in India, and again causing the blocking of the sunlight. So the dinosaurs die out, except for the birds, to be replaced by a very rapidly diversifying series of mammals, initially whales, bats, horses, elephants. And then the rise of Homo sapien can be traced back to the rodent-like survivors of the 65 million years ago asteroid strike. And many mammals survive further, less extensive extinction events in 56 million years ago, 37 million years ago, and 34 million years ago. And the common primate ancestor of humans, monkeys and apes, etc., emerged around 30 million years ago, with the first hominids emerging some 8 million years ago. Recent ice ages are thought to have been a factor in the development of hominids, according to the theory that colder temperatures favour the survival of infants with bigger heads, because bigger heads means less heat loss, and those with infants who stay longer closer to their mothers, which means that they have more time to learn. So this is how we explain the development of human beings. So I haven't taken 45 minutes, I've rushed it a bit too fast, and I've taken 35 minutes instead, knocked off a few billion years. There's no time in this 35-minute long tour of Earth history to look into the future and tackle the issue of climate change, except to say that hopefully this talk has shown two things. First, that the development of the planet and the development of life are intimately linked, and they affect one another. And also that change is central to the development of life. And I will conclude by just saying that we quite often hear people who dismiss the reality of human-induced climate change, arguing, oh, the climate has always been changing. But as we can see, those changes over a long period of time have been very substantial, including long periods which would be totally inimical to human life. The fact that the climate is always changing does not mean as well that humans cannot affect that changes themselves. So I think those are, for me, are the key lessons to learn. And with that, I'll hand back to Jim and we can go into a question and answer session.
Great, thank you, Paul. We've had a couple of questions. One was about the singing in the background, the birds. I did hear the evening birds. I don't know. The question was, do you have a budgie? And I know you don't have a cold budgie, but yeah, thank you. There was a couple of questions. One, it was about the first rock formations and the first rocks that were formed. And I'm not sure if Stephen came on just after you mentioned about basalt, but the age of the rocks sound like the first rocks formed were granite. So does that mean when we find granite, that is usually some of the oldest?
The first rocks to form was the basalt, because basalt is a rock. And also, in fact, one thing I skipped over things because I thought I was going to be short of time for this. The basalt, which forms the oceanic plate, the basalt is formed near the surface because it cools rapidly, being near the surface, and has small crystals. Medium-sized crystals are formed from the same molten magma that formed dolerite, and below that, large crystals form gabbro, names which will be familiar to most people. Common climbing rocks, dolerite and gabbro. So those are the first rocks that formed. Then the development of the granite was a subsequent, but still very early development, whereby the base of the plate would melt. So the rock of a basaltic chemical makeup would melt at the base of the plate. And when it melts, it is less dense than the solid material. So it then starts to move towards the surface. As it moves towards the surface, it begins to cool. And the first minerals to start cooling and solidifying are those that form the granite rock.
And that's why the continents came after, and that's why the continental rock and the granitic rocks appeared subsequently after the basalts had begun their process and the tectonic movement.
Yeah, that's correct.
Interesting.
And the granite islands were volcanic islands, which is presumably why the base of the plate melted at a particular point, was because it was close to a hot spot with the core below.
I mean, how widely understood and accepted is that as the theory?
I'm not sure, to tell you the truth. I won't answer that one. I can't say.
Because we're looking so far back in history. And I know some of the oldest rocks are 3 billion years old or so. Are they on the planet?
3 billion, yeah, well, more than 3 billion more years old. More like 4 billion, some of the oldest. But the basalt is all recycled, so none of that has survived. So it's only continental rocks which have survived. And when they melt, when they solidify, then some of the minerals within them, zircon, if it contains zircon, will solidify, and they can measure the half-life and tell the date at which those zircon crystals solidified. And that is the main source of dating of rocks, of ancient rocks, is zircon. And
it's interesting.
There are one or two, and they are tiny fragments that they found, which solidified 3.5 to 4 billion years ago.
So that might answer a question come regarding some of the earliest rocks on the surface are cratons in Canada and South Africa. Is that correct?
Yeah, craton is a name for a geological feature.
Okay. Rather
than a rock type as such.
And so they're the oldest known rocks because of this radio dating. But then Torridon, I mean, up in Scotland, the Torridon gneiss is meant to be amongst the oldest rocks on the planet as well.
Well, it's about 3 billion years old, the Lewisian gneiss. The oldest of it is 3 billion and goes down to about 2.5 billion years old. But Siberia, Canada, Australia, the Baltics, there might be one other, they are the oldest known continental features, the cratons.
A question about what is a Deccan trap eruption?
Right, okay. Trap is a term used to describe volcanic flows. So you have a flow of lava, then another flow on top, then another flow on top, and so on. And those are known as traps. So it's known as trap topography. And you can see this very clearly, for example, in the Lake District in various places. And then the Deccan traps are these great vast flows of lava that occurred in the Deccan area of India. And they were absolutely massive, probably the biggest volcanic eruptions or series of eruptions that were known, putting out all this material which blocked the sunlight as well. You know, the gases that were given off blocked the sunlight for years and led to one of the mass extinctions.
So when was that, the Deccan traps? Do you know, do you have a rough? You said it's one of the 5 main. Yeah,
65 million years ago.
That's Cretaceous.
When the 10-kilometer wide asteroid struck the Earth.
Right.
Mega tsunami, massive fires, clouds blocked the sunlight, and the Deccan traps were about the same time. Now,
Right.
there's no suggestion necessarily that the asteroid strike caused the eruptions, because the processes of plate tectonics are carrying on regardless of what's happening on the surface.
And that was the famous KT boundary, wasn't it? I think that
would be, wouldn't it? Yeah, that age.
Yeah.
I think, yeah. When the
question
dinosaurs died out.
A question here on a evolutionary question, but more biological, about why was it? You talked about the Carboniferous and the evolution of the large insects, but do you know why the insects were the first to develop?
I don't know why they were the first to develop. No.
Arthropods, jointed limbed organisms, aren't they, with hard exoskeletons mainly?
I'm out of my comfort zone.
I thought it would be. I'll get you to enjoy the green plants one day, Paul. There's one question just here about you mentioned the snowball Earth, and you mentioned ice ages and the more recent ice age, and there's this history of the world having these periods of ice house Earth, or these ice worlds. Question is, do you know what the triggers for causing ice ages? Do you know what the build up and the lead up towards these events? And will there be any more?
Well, if we start the most recent ice ages, what we have is a series of different features which occur to do with the rotation of the Earth and its wobble and so on. And you've got there's a 10,000 year cycle, a 20,000 year cycle, and a 100,000 year cycle. And when you get all those three different cycles all working together, pulling together, then you get really cold periods or really warm periods.
They're the Milankovitch cycles.
They're the Milankovitch.
I think he was Serbian, wasn't he? He came up with that. Yeah, no. So that's widely accepted, and those eccentricities are widely accepted as contributing, aren't they, towards the climate? The world's climatic factors.
Indeed. So you get ice age, you get a warmer age, you get another ice age. And I see somebody's asked, will there be any more? There will be. But if you go back to the snowball Earth, then it's a bit more difficult to define, as far as I can see, what caused those snowball Earth situations to arise. And it's something to do with the continents, reducing the amount of, or increasing the amount of plants operating on the edges and affecting the atmosphere.
I mean, that's something you alluded to at the beginning when the first life forms started evolving. You mentioned that there was a link with the climate and how there's instabilities or the climate began to change when there was more life formed on Earth as well. So that there may be a link with that and the atmospheric gases. And I mean, someone's mentioned here sunspots, and those cycles have an impact on world climates as well. And there's many factors, aren't there, that contribute to that.
I don't know about sunspot cycles, honestly. How they wouldn't be regular in the same way that our eccentricities of the Earth movement are. So they would be more an external force than one that is regular part of the Earth processes.
Yeah.
But it's possible, I suppose, that it could affect the snowball Earth situations.
Yeah. No. The glaciations and ice ages take millions of years to form, don't they, and to come into these cold cycles. The last one, the fifth one, is from 2.6 million years ago, isn't it? And it's been with permanent ice on one or both of our poles, and that's what is defined by geologists as an ice house Earth or an ice age, isn't it?
Right. Yeah. some people call it, rather than a snowball Earth, call it a slush ball Earth. So again, there's something, because there's no real evidence that survives of the rocks, sorry, of the ice itself from those incidents. What survives are glacial, typically glacial rocks, till or tillite. It's till, and then when it solidifies, it becomes tillite. What used to be called boulder clay, which the glaciers push forward and leave, and they're able to date some of those ancient tillites and this is where they get the dates from. But the ice itself obviously doesn't survive because it melts. So having to read the feature, the time through another feature. So there's a lot of uncertainty about these things. You've got to discover the tillites. You've got to be able to date them with reasonable degree of accuracy on which people can agree.
That's right. And it's really interesting how you have to go to a place like the Sahara Desert to find evidence of these ancient tillites.
Yeah. And they are in awkward places to get to. They don't tend to be, up the road.
No.
Close to the university sort of thing.
Yeah. There's a question about recommendations for field guides. I know you sent an email to me earlier with some reference materials.
Yeah.
So I'll share the reference materials following this. I'll send an email out through Eventbrite for everybody. And I mean, there's lots of field guides, and it's geology is it's very. I mean, I still find it hard in the field to look at rocks, but to actually try and identify things in a simple way for the layman, it's not always easy to find that accessible form of information, is it? I mean, there's some great simple fold-out charts and keys. The Field Studies Council, for instance, the British Geological Society have information which is really accessible and easily readable. You've got some books which are pretty handy field guides.
I would recommend them.
I thought I should mention them, Paul.
But I think the best field guides, in a way, are geology maps. The 1 to 50,000, and if you can get them, the 1 to 25,000 maps, and also iGeology, which you can download from the British Geological Survey website on its main page. iGeology, you can download it, and I've had this on. I've been, doing workshops out in the field, and you say this, and some young person will say, "I've downloaded it," so it's a nice, easy process to get. And then with your mobile phone, provided you've got a mobile signal, you can tap it, and it will tell you what rock type you're standing on. The only limitation is that the granularity is a bit rough. So it will miss out small outcrops, which you do see on the geology maps. So it's an introductory thing. It's a very handy thing to have. And of course, it doesn't work if you haven't got a mobile signal, which for a lot of mountaineers is going to be what will happen, because you go to Pen y Pass here and you don't get a signal.
How easy is it to get hold of geological maps?
Very easy. From www.geosupply, we'll add it to the list, www.geosupplies.co.uk. And there's a couple of others as well. I have heard, I don't know whether it's true or not, but I did hear about a year ago, I heard that BGS is going to stop producing paper maps, and it's all going to go to online maps. So get them now while you still can, because they are handy things to take out into the field. They are, if you do buy them, what I would recommend as well is laminating them using book cover, because they aren't, the paper they're printed on is not as durable as the OS maps. And as you open it and fold it and close it and so on, then you will begin to break up at the corners. So I would suggest if you buy a geology map, then laminate it to protect it, and it will last for ages.
Well, there's one question I missed earlier, looking back up through the chat. And your thoughts on the 8th continent. What are your thoughts on Zealandia?
I'm going to jump that one, I'm afraid.
You've heard it being mentioned?
I've heard it mentioned, but I haven't looked into it because it's a long way away.
The other end of the planet, isn't it? So, well, I think if that's the end for the questions, I know we're a little bit shorter today, but interesting insight into it's just it's fascinating evolution of a planet, of how we've got to where we are and how the planet became green, and you know, plants and animals emerged onto the land, and we are where we are today. So Paul, thank you very much for sharing your knowledge with us there. I'm just on a different computer today. I just want to finish off with just the last slide from me, just to say that in this series, there are just 2 more talks coming up. Next week with Sophie Lee is full. I've checked today, so that is a popular one. So I'm afraid if you haven't got a ticket for that, there I can only have a meeting of 100 people with my Zoom account. But then Wild Food and Foraging is the one that we'll finish with. I'll be leading that one in a couple of weeks' time. So that's where I'd like to finish tonight with. So thank you all very much for coming along and attending. Paul, thank you very much again for presenting. Awesome. And I wish everyone a lovely evening, and hopefully we'll see you again soon. Okay, bye-bye for now.
Good night.
Bye.
Bye.